All right. My God.
Okay, good morning. Can you hear me? Can you please confirm you can hear me? You can hear? Yes? Okay. Good. So now what I hope is that it's actually going to use also. Yeah, okay. I'm just going to try to make the recording from the computer instead of the laptop because from the iPad, because I wonder if it's going to pick up the right sound, but at the same time, if you can hear it, then theoretically, yeah, it should be recording. Well, maybe I just leave it like that and then hopefully it works. In any case, it's not a big deal. So today we are going to talk about something fun, which is going to, I think, be quite interesting for everybody because it's going to have to do with surrogate models and how to use them in practical settings and how to build them. So first of all, what they mean, why we need so-called surrogate models, what they are here for. I don't know who among you listened to my talk that I gave in Exeter. I recommended that you do that, but I don't know if anyone did it. Could you please confirm if you did that or if you didn't do it? Anybody could tell me if anybody listened to the talk that I gave in Exeter last week? Yes or no? Can you please just write yes or no in the chat so this way I know who I'm talking to, because it helps a bit to know what I'm going to. So apparently no one understands the question, or so did you guys listen to? No. Okay. Right, so I'll let you then do it. So you are not online, so what I'll do is I'll share the link and I will upload it to YouTube on my own channel. For now, it's on the university's channel, not on my channel. So it may not be very easy to work on that. So perhaps anybody else looked? So do the others do not understand the question, or is it why do I have no answer to the question? Is it because the question is unclear, or is it because the answer is no? It's fine if it's no, it doesn't really matter very much. It's just that we would have saved time, that's it. Because I gave a 1 hour talk, which has a lot of information in it, and I think it would have been quite nice. Yeah, because if I have to give this talk again now, it's going to be a little bit of an overkill, I think. Right, so apparently this is not really. Yeah, all right. So, well, then in that case, I'm going to simply talk to you about what I talked about last time in this, in the talk that I gave. I was not planning to do that because I hope that you had listened to this talk. So now I'm going to look for the presentation. Sorry about that. But now I'm going to have to share this screen and not the other screen, which will of course create a problem. Let's see how that goes. Can you see that? Could you please, instead of using the chat, just speak out loud, because I can't check every window at the same time. So just tell me yes or no. Can you see the screen? Right, so I just assume you see the screen, because I can't see anything else. I don't hear anybody saying anything. So we are I'm just going to start telling you about why we need surrogate models. So I see there is only one person here. Is that the case, that there is only one person in the room? A bit perplexed, I have to say. Let me check on Signal if there is a problem. Okay, anyway, I'm just going to give the talk assuming that everybody's here and people will or not listen to it later. That's fine. All right, so what we're doing is we have the following case, and this is a situation which arises in many cases in industry or in research, in academia, everywhere at the moment, and for a few years already, probably a decade even, as the amount of information or data which we are able to capture from the world, the amount of information is increasing. So we are in a situation where the amount of information is very large, and that information can sometimes be sufficient to figure out what the connection between an input and an output is. We are now able to collect a lot of data. The data is collected using all sorts of sensors that are embarked upon structures. They are used using social networks, for example, or internet data, web data. They can be scraped from the web. There is a huge amount of information out there. And this is what we think about as data. So data can be multiform. It can be of high quality, low quality. It can have several shapes. It can change over time. It can evolve. And sometimes you have a huge amount of data. That's the case on the right-hand side here. But sometimes you have a very low amount of data. That's the case in the left-hand side. And typically what we had been used to before this so-called data revolution, in a way, which is really not an overstatement. It is really the case that the amount of data generated in the last 10 years is humongous compared to what had been generated before the last 10 years. And that's not really slowing down, it's actually accelerating and keeps accelerating. So the change in paradigm is that we used to be sitting down in an office, essentially, and trying to derive models about the world and trying to figure out how to write those models in terms of partial differential equations. This is what we've been talking about until now. Until now, we've been writing equations thanks to conservation laws. So we learned how to write conservation laws that then lead to writing partial differential equations. They are mathematical descriptions of the world we're trying to model. And these have also parameters. And these parameters are typically unknown. But then we can use real world data, which is gathered a posteriori to figure out which parameters should be given more importance, which parameters should be given less importance, and then what is the value of those parameters. So there are quite a large number of ways that you can model mathematical, let's say, a lot of ways that you can model physical reality, so the physical reality around you, or a system, or a set of systems, or people in real life, and so on. So there are lots of ways that you can do that, and you can do that by a priori writing equations. This is what we've been doing until now. And now the other extreme, which is on the right-hand side here of the spectrum, is when you have no equation whatsoever. So just to give you an example, on the left-hand side, we talked about all these conservation law, Newton's cooling law, Newton's law of motion, everything, Maxwell's equations, theory of relativity, and all the rest. Right? So all these things, they are equations that people sat down, looked at the world around them and said, okay, it seems like things are working this way. And then they wrote that down, and then they went out to do experiments. And doing these experiments, they saw, okay, my theory fits with experiments. For example, Newton did that. They looked at a lot of cases, and they saw that Newton's law can explain a lot of what you observe in the real life. But then what happened is that people started to look at galaxies and the cosmos and so on. And they also started to look at things that are very small. And then at that point, the model that Newton had written broke down. So if things are very fast or very large, Newton doesn't describe the physical reality in the proper way anymore. And therefore, you need to have an alternative view of the universe. And this is the way, by trial and error, that you become convergent in terms of what model to use and when. This is the basic idea. So this is the left-hand side. First, you write equations, then you check them. Of course, you are inspired by the data around you. You're not agnostic to what you see. So it gives you ideas, it gives you some sort of intuition, what could be happening. But then you think out of the blue about the model that is going to describe what you see. So the right-hand side now is where we are, let's say today, and where we will be even more tomorrow and in the decades that are coming. We are in a situation where, if you look at the right-hand side here, this is some neurons that are firing in the brain of a very small worm. So the good thing is you can count the number of neurons in this worm. The worm is called C. elegans. And this is used very much in biology because you can actually count the number of neurons and you know exactly how they are connected. And therefore, it's super nice because you can look at the way in which the brain, let's call it this way, of this little worm is being used, let's say, or being activated. Okay, so that's basically what is going on with that part. You can also think of that, so this is in that case a network or a graph that is connected, and these connections mean something biological. Okay, that can also be a social network, for example, and I'm only using networks because it's easy to figure out what happens, but I'll give you other examples too. So if you look at Instagram, for instance, you look at Instagram and your question is, how can I use Instagram data to help companies place advertisements or commercials in the best possible place? geographically. So you'd like, for example, you work for a certain company that has logos, for example, I don't know, Coca-Cola, for example, and your goal is to know where should I put some ads or commercials for Coca-Cola. So where should I put these little placards on the walls or on the streets, on the bus stops or in the pub or whatever, so that people have a highest chance of seeing it. What they do in practice is even more than that. They actually try to figure out who is going to go come across these ads by using the phone network to figure out what connections to the relay are taking place in order to have an idea of the profile of the person. Of course, you don't have the identity of the person, but you know if they are high income, low income, if they work in banking, if they, if they were born in 75 or 88. And all that information can help you place commercials at the right place. So this is called business intelligence. People do that a lot. And they use data that they get from social networks or data that they get from the cell phone towers to which our phones are continuously connecting just to figure out where you are, and also in order to be able to place phone calls or use 4 or 5G or whatever other means of communication you're using. So what they do is they just look at this data and they try from that data only, without any model. There is no model saying this person will pass by that lamppost at that time or will stop at that bus stop. There is no model saying that the probability of having a banker coming across this advert of a luxury watch in front of a bus stop is 80%. You don't know in advance. There is no law. You cannot write it as a function. You can only observe it as a fact and then come back and try to figure out how you got to that fact. But first you have data. So you have huge amounts of data, and that amount of data is very important in order to figure out what's going on in the model, in the problem, in the physical world. All right, so but in all cases, you have an input and you have an output and you have a function or functional F, and this is the thing that you are trying to figure out, right? You're trying to figure out what is linking the input to the output. So the input in the latter case could be position of the person, and the output could be probability of that person being a banker, for instance. So that would be one thing. Or probability that such and such type of person will enter such and such place at such and such time. On the left-hand side, it's much easier to understand. The relation is very easy to really follow. You have a case where, okay, what do I observe? I observe, for example, that we have sensors on a plane, and we are interested in figuring out if the plane is going to be able to take off again, or if we should send the plane for repair because the cracks are too large. So this is basically the problem here. Okay, so we are on the left-hand side in a case where we have equations, we can write them, and we have then data that's able to help us verify or validate rather these equations. So what is really interesting, what you see on the left-hand side is Antarctica and the deformation of Antarctica. And on the right-hand side is this neural networks of C. elegance's brain. And until now, I think until the last 10, 20 years, we were really mostly in hypothesis-based models where you make hypotheses about the world like Newton, and then you see if a posteriori that works. The data-driven models, you do quite the opposite. You are in situations where you have huge amounts of data, but you have no, let's say, equation that's going to govern this data. You have a lot of data, but you don't know what to make of it. And what is really interesting, what I'm particularly interested in, and a lot of my colleagues as well, are what you can call adaptive models, which are models that are neither only equation-based, meaning hypothesis-based, where you write down equations and then you identify the parameters, but they are also not data-driven models because you don't have only data, you have a bit of understanding about how things work, but you lack details. So you don't know what the parameters might be. You may not even know what should be taken into account in that model, because it may be that some parts of the model are activated, but other parts are not activated depending on the circumstances. So for example, if you remember the coffee cup, it could be that for certain temperatures, the convection becomes more important than the advection, and that the radiation and that the standard cooling rate. So it could be that you have changes in the way the model works. So that is something to take into account here. So these are adaptive models, which start in a way, you can say Newton's law or Newton's cooling law, and then you look at something in the data and you say, for example, you start measuring the temperature in the data, and then you say, oh, no, the temperature that I measure does not at all fit Newton's cooling law, so I must be forgetting an important part of the problem. And then I add a point, I add something like, I don't know, maybe radiation or maybe convection, and so on. And I add parts of the models on the go. And this is the way that I'm trying to describe the world in a better way, in a more precise way. Let's put it that way. So that is what everybody is now interested in. And we are in situations where we have either less data or more data, and that you can move your cursor left or right, depending where you are. And we are now never in cases where we have small data. It's very, very rare. Most of the time, we have data. In biological systems, it could be that the data is not very easy to get, very expensive, but we have data. And one of the big questions, which we are now trying to answer, in particular in biology with my partner Anna Grunewald and other colleagues, is to ask the question, how exactly are you solving that problem of data? So next week we're going to be at Columbia University to discuss that with colleagues there, Anna Monzel, because we would like to come up with a way to have some sort of large language model to which we could actually talk in order to help figure out what experiments should be done in order to minimize the uncertainty on certain quantities that we are interested in. So if you see what I mean by that, the question would be, okay, let's say that you have a system, any system. For now, we are interested in systems that come up in biology. So that would be something like stem cell research. So you start by growing stem cells in a dish. These stem cells grow, but as you can imagine, they grow in a way which is not always perfect. You have cases where they actually where the cells die because they are not sufficiently fed with glucose. You have cases where the cells might not transform into what you like them to transform into. So it could be, for example, that the cells are supposed to become neurons, but they suddenly decide to differentiate into microglia, which are other cells, or maybe astrocytes, which are still other cells, or maybe they don't even differentiate at all in what you like. They differentiate into fibroblasts, which are the cells on the skin. So anyway, you don't know exactly what's going to happen, but you'd like to be able to say, I'm going to write my protocol down in natural language in the way I write normally. So when I do a lab report, I write everything down. When I do an experiment in the lab, I'm sure some of you do a lot of experiments, maybe you do mechanical experiments or thermal experiments or magnetic experiments or electromagnetic or whatever experiments you make, microscopy, whatever, you always have a protocol. You don't just do that randomly and just do one thing on the right, one thing on the left, and hope it works. So you do things in a very structured manner. You put that in a lab book. At the end of the day, you check the lab book. Next time you come into the lab, you read this lab book and you say, okay, that's what I did. Now I remember where I was, and then I start again from there. So everything is very clearly established. So what we would like to do is to have an approach where you, in fact, write these things down in natural language so that you can exactly provide the system with a detailed knowledge about how you perform the experiments, so that it's not something completely randomized. And when you try to then optimize the system, optimize your experiment, you have the actual data of what you did, and you can compare two different experiments in a very rational and quantitative way, as opposed to being very vague about, oh yeah, I remember vaguely I did this and that, and this was this protocol and that protocol, but not being very precise. Everything would then be written down. And then you could compare the quantities of interest. For example, if you're growing some cells, you could say, okay, this astrocyte, which is this cell with the little branches, looks like a decently healthy astrocyte. I'm happy with that. So I'm going to say that this has a mark of 8 out of 10. And I'm going to label all the astrocytes by hand. So it's going to be supervised learning. I'm going to tell the algorithm, this is a good astrocyte, this is a bad astrocyte. And then now I know what protocol I use to get to this good or bad astrocyte. So all this information is now encoded. And the beauty with large language models is that you do not need to keep the information in terms of words. You can encode that in terms of numbers. So at the end of the day, you're going to have two situations, let's say two experiments. One will be one vector in a certain space, the other will be another vector, and you'll be able to compare the directions, the relative directions of these two vectors. And what that tells you is whether two experiments, let's say, are close if they are mostly collinear, or if they are very different, if they are mostly orthogonal. So that is an idea that we are now pushing, and we think it will work because I will show you examples later that are showing, give me a second. Examples that are showing that this can work from chemical engineering. And this is the work of Jeremy, Eleni, and Paris over several years. Eleni Koronaki, who is now working at LIST in computer science. So now the good thing about that is that you can think of the problem as something which you can quantify. So for example, you would like now, next time you do the experiment, let's change from cells, we can take another example. Let's say that you make a microscopy experiment on some sort of metal or something, or maybe you go in farmlands in Luxembourg and you try to figure out what is the occupancy of the fields, how many cattle you have, where, at any time. So you're going to do your experiments. You're going to measure everything. You're going to put that in your lab book. I did this, I did that. I went to this place. I talked to this farmer. I went there. And then you write everything down. You have all your data and everything is cool. Now, next thing you do is you're going to compare these different vectors in that new space. And you would like to say, how can I optimize the system such that I know which place I should visit next in order to minimize the uncertainty on what I'm interested in. So if you're looking at farmers, you may be interested in having the densest possible distribution of cows in a certain area because it's more efficient. Or you may be trying to figure out if you need hedges between the different fields. If you're looking at microscopy, you may want to maximize the legibility of a certain feature on the microscopy image, which you want to maximize. So every time you do that, there is always a debate whether you should do more experiments, and if so, which ones? So what fields should you visit, what farmer, what area in Luxembourg, what microscopy image should you take, and so on. All these questions, what experiment should I do, when should I do it, what conditions, and so on. These are design of experiments questions, and these are very interesting questions. They are more and more interesting nowadays because not only can you do physical experiments, but you can also do numerical experiments instead. And then comes the question, you probably thought to yourself already, if I'm using ChatGPT, I'm actually using huge amounts of energy. This is not very sustainable. If I ask one question or even I add one word, like, or two words, thank you, it's going to require a lot of processing that I actually don't need. So this is costly. It looks not costly because ChatGPT is relatively cheap, but it costs a lot more to run than it does to use. So what you pay is a very small fraction of what they actually spend. And so this is really not sustainable. This is a bit of a bubble in a certain way. And so we know it's not going to work like that forever because the amount of energy used is really huge. So when you make a decision, should I make one more physical experiment or one more computational experiment, be it large language models, which is a very easy example to figure out, or should it be, maybe should I simulate the system instead of measuring it? For example, about these cells, if they are growing, we have models of cell growth. We can model that. For example, my PhD student, Miriam, has been working on cancer growth, and she can model the growth of cells under certain conditions in the body. So should we make one more model, or should we take one more MRI, for example? You know, the MRI is costly, but the model is also costly. And to each of these two choices is associated a level of uncertainty. In other words, perhaps the MRI has a certain resolution, and perhaps your computational model has a certain error. And this is why we talk about modeling error and discretization error so much in these two courses, in complex systems analysis from a discretization viewpoint and from a mathematical modeling viewpoint, because that is going to define whether or not you should do more physical experiments to decrease uncertainty, but also with a certain level of accuracy, which you cannot really control because you have noise and that's the way it is. And should you perform more computations because these computations are maybe not less uncertain because at least you know what error you're committing, but you don't know the parameters exactly. So you would need to be sure to be able to actually identify these parameters in a precise way, which is going to be done by experiments. So that sort of interplay between what should be the computation I make, what should be the experiment I make is super important. And this is really the state of the art today of what people are working on in terms of research in that field. People are really thinking, how do I decide what experiments do I make compared to what I do with the computations. Okay, so that's going to be the introduction. I'm going to show you a few practical examples, and then I'm going to show you a bit of theory. So just hang on in there while I move to the other presentation, which I hope I can. Yeah, okay. Model reduction, multi-scale presentation. Yep, let's do. Let's look at that. And then instead of sharing Keynote, I'm going to share PowerPoint. Where are you, PowerPoint? What I'll do is I'll stop this recording.